Alright, hey y'all, it's Miss Summers with your notes today on indicators of water quality. Before we get started, I want to show you how you can set up your notes to make it a little easier on yourself. Alright, we're going to be looking at 6 different indicators of water quality. So you could take a table, or you can make a table in your notes. The heading would be indicator. We're going to learn what each word means, how humans change that particular indicator, so like how we make it worse, and then how that affects the environment or ecosystem. Oh, not effects, affects. Thank you. All right, so we're gonna have 6 different ones here. You can type these up, you can write them down, whatever, as we go along. All right. All right, so let's start with our first indicator of water quality, and that is turbidity. All right, here is our definition: a measure of how cloudy the water is. All right, so water can be clear, it can be dirty. That's what turbidity measures. All right, it's measured in this unit called NTU. Basically, the higher the number is, the more cloudy it is. All right, the lower the number, the more clear the water is. So ideally, in a healthy ecosystem, generally the turbidity is fairly low. All right, the Mississippi River, especially at the end of it, towards like Louisiana, is an example of high turbidity. And this is because, remember, the Mississippi River has a lot of tributaries, a lot of rivers adding to it. So all the pollution from those rivers add up and accumulate in the Mississippi. All right, causes of turbidity or how it changes. All right. Erosion, remember, humans can affect erosion by removing vegetation, so there's more soil being lost when it rains. Waste discharge, if you have like a sewer pipe break or something. Algae growth and urban runoff. So how does that affect the ecosystem? Why do we care about the water's turbidity? Well, the turbidity affects how much light gets through the water. If the water has a high turbidity, water plants die off because they're not getting enough sunlight. And if the water plants die off, animals will then die off due to starvation. The food chain isn't complete. Or, more directly, aquatic animals can suffocate on these sediments. Okay, it's essentially like if you were breathing like in a smoggy place, like a place that had a lot of smog and a lot of pollution in the air, that would irritate your lungs. With a fish, all right, they don't breathe air, they get oxygen out of the water through their gills. If there's a lot of dirt in the water or a lot of sediment in the water, that affects their gills and their ability to get oxygen. All right, so that's our first indicator, turbidity. Our second one is our pH. All right, pH is simply the acidity of the water. I do want you to know that the lower numbers from 0 to 7 are acids, and everything above 7 to 14 is a base. All right. Surface freshwater usually has a range of pHs, so it can be anywhere from 6.5, which is right about here, to about 8, which is right about here. So normal range. You see that in that little diagram. All right. Changing in pH can be a real problem. It can show that something is wrong with the ecosystem, something is being added that should not be. All right. So how do humans change pH? Well, pHs do change naturally over time. They have the ability to. If something in the environment happens like a volcanic eruption, certainly that can change the pH. But also dumping of waste, all right, dumping things that are acidic into the water, or farm runoff, all right? How that's going to affect the ecosystem? Most aquatic life lives in a range of a pH range, all right? It can only tolerate so much change before their cells start to die. If you take in biology, you probably remember that, like, something about enzymes and how enzymes denature or break down. If the pH is outside of the range, that's essentially what's happening here. If you haven't taken biology, that was a preview. All right, here's a nice little graphic that you could see. The pH tolerance of various aquatic species. Light blue areas indicate pH levels which cannot be tolerated. That means they die. All right, so here, Remember, the lower numbers mean more acidic, the higher numbers mean less acidic. All right? The animals that can't tolerate acidic, super acidic water, things like snails and clams, all right? You might say, well, frogs can survive. That's really cool. Frogs can survive if the pH is down 4. Okay, let's say that the pH does get that low. The pH of the water does get down to 4.5 or 4. All right, the frogs are okay. But remember, what do frogs eat? Frogs eat bugs. They eat flying insects, like the mayfly. Well, the mayfly can't tolerate anything below 5.5. So even though the frogs can survive in this environment, they're going to die off because they don't have a food source, and that's a major problem. All right. Our third indicator, dissolved oxygen, it's how much oxygen is dissolved in the water. Wow. That's enlightening. Not really. All right. Again, different species have different tolerance levels. How we change dissolved oxygen. All right. A direct human activity, discharge from sewer pipes, that would decrease oxygen because we're adding more bacteria. Bacteria take up oxygen too. So if we increase the bacteria, that's going to decrease the oxygen. All right. If we increase the temperature of water, that will decrease the amount of oxygen. All right. If water is moving rapidly, it's moving quickly, that generally adds oxygen because it's mixing it up with the air. All right. Now, people don't generally make water move more rapidly. We generally make it slow down by building dams. So by default, if you slow water down, you're going to decrease the oxygen as well. All right. You don't want dissolved oxygen to drop too low because otherwise the fishies die. Okay. Because all living things, or most living things, not all of them, but all animals require oxygen to live. So if you don't have enough, they're going to die off, and then your food chain gets messed up. Dissolved oxygen can also be too high for people, not because it's like dangerous for us or anything, but because it damages water pipes. All right, the oxygen is going to react with the metal and cause rust, and that's not a good thing either. All right, our fourth indicator, temperature. All right, you probably had this on a fish tank, especially if you have a tropical fish tank. This little thermometer tells you how hot or cold something is. So how do we change it? How do we change the temperature of the water? Well, the source of the water changes the temperature. So if it's from like a high elevation from somewhere up in the mountains, it might be colder. We don't really change that. But we can change this, shade from the shoreline. All right, if you cut down a whole bunch of trees that used to keep the water cool, well, now it's exposed to the sun, it's going to get hotter. Also, this thing called thermal pollution. Thermal pollution. All right, thermal means heat. This is just the act of us heating up water and then putting it back. So the nuclear power plant like this here, all right? Nuclear power plants are actually like really like clean as far as pollution is concerned. Like they don't make carbon dioxide. They don't make any like leftover products that get dumped right back out into the environment. The problem with nuclear plants is they take in water from a lake. They heat it up using the nuclear fuel. All right, the nuclear fuel doesn't touch the water, so it's not like the water is radioactive. But the water gets really hot. That creates the steam to run the power plant, and then they put it back into the lake. All right, so this water is warmer than it was when it went in. And even if it's only a little bit of difference, even if the temperature only went up a little bit, that can still have a big problem. All right, we're going to watch this little video of this show called River Monsters. It's like one of my favorite shows ever. Hopefully you've seen it. If you don't know the premise, it's basically this guy and he goes around the world fishing for like these crazy fish, and he's in Russia in this particular episode. All right, and they find these fish that have died. And I want you to look at the little experiments they do. Please work. Please work. Yes, it's working. Fantastic. All right, we're going to skip to minute 29. Okay, so he's out So he's out in the river with a bunch of scientists, and they find a bunch of these dead fish. Okay? So, listen for how temperature played a part in this. Play. Dead fish.
This is actually quite spooky. It looks like a migration of fish. There's all these fins sticking out of the water, and what it is, it's salmon upside down, and their tail fins breaking the surface, and they're all sort of drifting down with the current, and they're all dead. Of course, it's normal for salmon to die after spawning. I wonder if that's what's happening here. And even more of what we're seeing too many of. Dead salmon, and a lot of them now in fairly advanced stages of decomposition, which sometimes makes them fall apart and nicely go through the net. Other times you just get endless smelly fragments just all over the place. Just seeing all these dead fish. I mean, it's unpleasant just from a visceral point of view, just the smell of death. This one is pretty horrible. That was a male fish. It looked like that fish hadn't spawned. And the more we set our nets, the more I get the feeling that something out of the ordinary is happening here. Some of the ones that have actually broken open because they're so decomposed, they've still got eggs in, they've still got lots of eggs in. So this isn't normal. Normally dead salmon have no eggs, they've sowed the seeds of the next generation, but this isn't a normal situation. There's something going on here. Back at the scientists' research vessel, taking a break from netting, I find some salmon still alive close to shore and decide to perform a test using a thermometer borrowed from the scientists. So there's a very dramatic difference in water temperature. I could feel it with my hands, but according to the thermometer in the stream, the water was 10 degrees Celsius, 49 degrees Fahrenheit. At the mouth of the stream where the salmon are milling around is 15, 58 degrees Fahrenheit. And then here at the side of the river where the dead salmon are is 25, 76 degrees. That's a massive overall difference of 27 degrees Fahrenheit.
Okay. So, back to our notey notes. So, how they knew the fish had died unnaturally. Alright, so clearly the fish died because the water temperature was too warm. Alright, living things can only tolerate a certain temperature. But they knew those fish had died unnaturally because they hadn't finished their life cycle. They hadn't laid their eggs yet. Alright, now why that's bad for the whole ecosystem. Okay, not just the salmon that died. Alright. First off, the salmon population obviously goes down, all right, but that's a problem because other animals rely on salmon as a food source. There's certain animals that only eat salmon eggs or salmon babies, all right? If those salmon all die before they had their babies, that food chain is now disrupted, and that's a problem. All right, moving on to our next our next indicator, nitrates. All right, a nitrate is something that's used in fertilizer. So here's your definition. Oops, go back. Fertilizer ingredient used in agriculture. So plants, people put fertilizer on plants to help them grow. The nitrates help the plants build the proteins that they need to be, nice and pretty and strong and all that good stuff. All right, what happens with nitrates is people put down fertilizer, and then that fertilizer gets in the water, and then algae uses the nitrates as food. All right, so the algae starts to explode. All right, and this is a thing called eutrophication. So write this down under nitrates. Eutrophication is when an algae bloom grows because of excess nitrates. So I'll say that one more time. Eutrophication is when an algae bloom grows because of excess nitrates. All right. So you might be like, okay, so there's a lot of algae. Like, algae's a plant, or it's not technically a plant, but it's a green thing. Other things eat it. Like, why is that a bad thing? Well, here's why it's a bad thing. The algae the algae bloom will cause a reduction in dissolved oxygen, so there will be less oxygen. Okay, when eutrophication happens, the oxygen goes away. That's all you need to know. And that leads to the death of insects and fish and basically everything. So here's a little storyboard that shows you how this happens. So here's our farmer. Here's Farmer Brown. Farmer Brown's putting down the nitrates, the fertilizer. The rain comes. This fertilizer runs off. It runs off into the stream, into this pond. Because there's extra nitrates, the algae grows on the surface. Now, first off, this is blocking sunlight from getting to these plants, so these plants die off. When this algae dies, the bacteria that eat it up, that break it down, suck up all the oxygen. So that's why there's no more oxygen. All right, just know that extra nitrogen makes a lot of algae, and that lot of algae ends up taking up a bunch of oxygen, and everyone dies. All right? So which river has the excess nitrates? Clearly this one that these little children are playing in. Over to the left. All right, you see a lot of growth of algae and stuff on the surface. All right, that's blocking any light from getting down beneath. So there's probably not a ton growing underneath here. This one is nice and clear, nice low turbidity. All right, there's probably some nitrogen or nitrate in this water, but it's a healthy amount. All right, our last indicator are the bioindicators. Species used to monitor the health. All right, so these can be a group, a population, so you can see like how their numbers change. So one year I have 50 and the next year I have 75. Or you can look at the individual health. All right, you can put like little tags on particular animals. You can take their weight, their age, how healthy they are, all that good stuff. Amphibians are one of the best bioindicators because amphibians are special. They are called that because they live both in water and on land. So they're in the water completely when they're babies, and they go on land when they're adults. All right, their skin is also really thin. If like you picked up a frog, it has really, really thin skin, and it's kind of slimy-ish because it allows oxygen and other things to move across it. So if there's any pollution, these little guys get affected first. All right. How we use a bioindicator. This is a food pyramid. We're going to look at this more in a couple units. But basically, if something is affected in this food pyramid, it affects everybody above and below them. All right. So let's say that frogs are what's called secondary consumers. They don't eat plants, they eat bugs, and the bugs eat the plants. All right. And then birds eat the frogs. If something is wrong with the frogs, that means that these guys, the birds, are going to be most affected immediately afterwards. All right. If there's not enough frogs, there might be too many bugs. And that's going to cause a whole cascade of effects. All right. So that's how we use bioindicators. So we would normally do this in the classroom. We would break up into teams, but unfortunately we don't have that. But I want you to look at each of the scenario and determine which water quality indicators are most likely going to change. All right, let's see if we can figure this out. All right, a sewer pipe burst and raw sewage is leaking into the lake. Which indicator will change? All right, and it's okay if you have more than one. All right, oh, no, it doesn't say. Oh, I'm sorry. You have to listen to me. All right, if a sewer pipe burst, things that are most likely going to change. Turbidity, because like stuff is in the water now, it's cloudy, and dissolved oxygen. The sewage, the bacteria in the sewage is going to take up the oxygen. So probably those two. A neighborhood is building a creek, or a neighborhood is being built along a creek. All the trees along the stream channel have been cut down. What indicators will likely change? The more than one. All right. So this one, the trees are cut down. So that's going to cause an increase in erosion, which means more turbidity. The trees get cut down, which means there's no more shade. So increased temperature. And because the temperature increased, remember, that means less dissolved oxygen. All right, when water gets warm, it can't hold as much oxygen. So that one had 3. All right. And I think this is our last one. Yes, it is. All right. A farmer has a hard time getting their crops to grow, so he adds some fertilizer, which runs off into a nearby pond. Which indicators will change? Well, anytime you see fertilizer, you know nitrates are going to have to change. Nitrates increase, which is going to lead to eutrophication. All right. Which means there will be less dissolved oxygen. So nitrates, dissolved oxygen, and turbidity. Because there's so much extra algae from the fertilizer, the water becomes more cloudy. All right. So one thing, one action can change a whole bunch of indicators. All right. We're going to add on this part. Normally we would do this in 2 days, but I thought that was kind of silly given the structure we have now. So I want to run through part 2, human impact, real fast, just looking at how people change surface water, we already talked about how we measure the quality. So let's look at how we affect the availability and quality of water. All right. So now we are finished with that chart, so you can just write these down as you please. As you please. All right. You need to know the difference between non-point source pollution and point source pollution. Non-point, there's no point. There's no one spot where the pollution comes from. It's non-point source pollution, pollution that results from many different sources, usually carried by runoff. So non-point and runoff go together. So this is an example of non-point, all right? This river is polluted, but I don't know where it came from. It came from a whole bunch of places. Point, all right, you can point at a point source pollution. You can say, there's the problem. Pollution that can be traced back to one identifiable source. So this is, I think this is along the Kanawha River, which is where I'm from in West Virginia, I think. But here we have some sort of industrial complex, and we have clearly something being discharged here that's polluting the river, all right? Point source pollution is easy to identify, and therefore it's easier to fix. I could just knock on this person's door and be like, excuse me, you're polluting the river, please stop that. All right? And that would be fixed. But with non-point source, I can't hold one person accountable. So this is a lot harder to control. All right. So let's look at how people impact water in terms of amount. We know that global population is increasing, so the amount of water that is needed every day also increases. But remember, from the water cycle, the amount of water never changes on Earth. We always have the same amount. So we have to be smarter about how we use it, and we got to make sure we're not wasteful with it. All right? Humans can impact surface water and amounts of surface water available by building dams and irrigating. So this really good example, diverting water for irrigation can decrease the amount of fresh water available for people who live downstream. So this sea, the Aral Sea, it's actually, it used to be a lake in Kazakhstan? Question mark. Former Soviet Union. So the Soviet Union, back in like the 50s, they were in a kind of like an arms race with the United States. They wanted to be the best. So they're like, we need like some pretty heavy agriculture. So this lake is fed by 2 different rivers. So what the Soviet Union did is they built a whole bunch of dams and diverted that water, made the water go to a different place to grow cotton. Over time, that had a big effect. All right, as you can see, this lake is kind of in the middle of a desert. So because there was no water coming into the lake and there was so much evaporation, the lake bed completely dried up. So this is in 2014. It's almost entirely gone. There's very little of it left. All right. Even if we have a reservoir, we can deplete the amount of surface water. This is Lake Mead, which is a part of the Colorado River. And it's right outside of Las Vegas, which is a really heavily populated area in the middle of a desert. All right, so people are using a lot of water in an area where water isn't found naturally. So this is kind of like a bathtub ring. Water level in Lake Mead used to be up here. And to give you some scale, this is a boat. This is like a little boat right here. This is about a 30-foot drop that they've seen. So there's a real concern as how are they going to have enough water for everybody who lives in Las Vegas and the surrounding areas. All right. So we can overuse water. We can definitely, remember, we never get rid of the water per se, but we can make it go somewhere else. And that's the problem. All right, let's see how else humans impact the water cycle. Urbanization. So urbanization is a process where you make cities. Urbanization increases the amount of paved surfaces, so sidewalks, roads, things like that, and decrease the amount of soil. So basically, when it rains, all right, normally when precipitation happens in nature, you have some runoff and some infiltration. Well, because it's urban now, there's no infiltrating because pavement is impermeable. Water can't go through it. So all that water goes somewhere else. This produces flooding. All right, and give you an idea of how much that is. 1 inch of rainfall on an acre of asphalt, which would be like the size of the park, probably definitely more than the size of the parking lot, or the parking lot at school, excuse me. The parking lot at school is probably a little more than an acre, I'd imagine. Produces 26,000 gallons of runoff. When if it were in the soil, it would be no runoff. This runoff will contain dissolved pollutants from these urban areas like pesticides, so people like spray their house for bugs, oil, they change their oil in their driveway, and other pollutants from homes and businesses. So this is all going to end up running off to one central location, and usually it's like a river. So like these things here, you might see like the storm drains. They don't go to a water treatment plant. You put some water down there, it goes straight back into a river, which is why they say don't dump stuff in there. All right. Pavement absorbs more heat, which we've all probably experienced. The road gets warmer than the grass. Because the pavement is warmer, this increases the temperature. So going back to that indicator, the runoff is warmer. That's going to harm the little animals that live in the water. All right, so how we can help? Obviously, we can reduce the amount of pollutants we release to the environment. So obviously not this, not this. If you drive a car or you do your own car maintenance, all right, when you change the oil, you make sure that that oil gets to a proper recycling center and not on the ground. We can conserve water. We can reduce how much we use, all right? Remember, we only need a certain amount for like survival. Everything else is kind of extra. So we want to make sure that the technology that we're using is using as little water as possible. That would be a smart start. Things like Energy Star appliances like dishwashers and washing machines, all that fun stuff. Limiting how much water we use outdoors, especially during droughts. All right. So that concludes our notes for today. I know that was a lot. Your work is on Canvas today. You will copy and paste everything into a Google Doc, and then you'll click share, and you'll get a shareable link, and that's what you'll turn in on Canvas. All right, you know how to get in contact with me if you need to.